iffy without the visuals, but procedurally it's pretty straightforward. Because if there's a unit vector definition, which is a vector divided by its magnitude, then for a unit tangent vector, you're taking the derivative of a vector valued function and dividing it by the magnitude of the vector valued function, right? So basically you're looking for the vector valued function that would represent one unit, one quote unquote unit of the overall vector valued function. All right, so that's what all this is really talking about. All right, but specifically as a tangent. So what would a tangent represent? Tangent vector is any vector such that when the tail of the vector is placed at a particular point on the graph, vector v is tangent to the curve C. All right, so you have a curve. You have a vector whose tail is on that curve, all right? So it would be shooting off into space. The tangent vector would be the vector that's tangent to that, all right? So at that particular location, you're looking for a vector that is tangent. So if you're thinking in terms of a line from Calc 1, a tangent line, the vector would be the direction of that tangent line, all right? This process is going to help us flesh out what that would be as a measure, all right? So how do we do it? We start by taking the derivative, r prime of t, u prime of t, because for whatever reason, I opted to redefine as u in this case. I'll take that as a typo. I don't ever want to do that again. That's just, I mean, there was no call for that. I give a whole definition in terms of r, and then my first example is in terms of u, or solve for u, I mean. Just, that's my one big failing. Sometimes I can't get out of my own way with that. What are we looking at? 6t plus 2, comma, negative 12t squared, comma 6. All right, so I need the magnitude of that. Which is the fun part. I'll get you to look forward to trig at some point. It's just because, you know, this is basic algebra. That doesn't mean you want to do it. That's just ugly. It has no alibi. We're 24t plus 4 plus 144t squared plus 36. To the fourth. Bless you. All right, so it's not even going to simplify down that much. So 144 t to the fourth. That's a hell of a question.
44 t squared. Oh no, it's 16 times 2 and 16.
Oh yeah.
So it's 12t plus 12t, so 24.
Right.
Yeah.
So 144 t to the fourth plus 36t squared plus 24t plus 40. Yeah, that's just so beautiful. Look at that. Ugh, disgusting. All right, so T of T is going to be 6T plus 2. I'm going to write the negative 12T squared and the 6, each of which is going to be over this disaster. Just going to put a star at that.
Why don't you just put the magnitude of U prime of T?
Because I wanted to write a star. I thought that part was obvious.
You have to like assign it to the inside. Why can't you just leave it on the outside and we only have to write it once?
That's too easy.
Say it again. Sorry.
So why are you bothering to distribute your your magnitude of the derivative? Why don't you just leave it as the vector times 1 over that scalar?
I mean, how hard is it to write it over a star 3 times?
You can write it over a star once, so.
I mean, I consider myself to be a very lazy person. Even I'm not that lazy. I can make 3 stars.
It's a unit tangent vector, so you need it over each part.
Yeah, actually, that's.
You need it like that.
You do actually need it like that because.
You can't have everything over 1 because then it would be a unit tangent.
Right.
So it would be a unit vector.
Even if it was 1 over the magnitude on the outside, it still wouldn't get the job done. So, and we'll actually see it in the next one because this is my. All kidding aside, I said this before. I will get you to like trig because that sucked, and I don't want to do that again. But then you get to the trig one, you're like, okay, wait a minute, hold on. I think I got something here. R prime of T. Easy enough because we've done this like 5 times already now. So we're looking at negative A sine T and A cosine T. And then the magnitude of that the square root of the sum of the squares. So negative A sine T squared plus A cosine T squared. All right. Now, you can do all the math here, but I'm talking about the magnitude of this vector valued function. Now, this vector valued function represents a circle. Right? So when you're thinking about the magnitude of a circle, you're talking about really the radius. Right? So you can do the math, but the answer to this ought to be what? A. And in fact, if you do the math, you'll get A squared sine squared T plus A squared cosine squared T, which is what we got in the previous 2 problems or whatever it was. Factor out the A squared to make it the root of A squared, which is A, and the other part will go to 1. All right, so you're going to get an A algebraically, or you're going to get it intuitively, but you're going to get A. All right, so when we get T of T, the unit tangent vector, we're taking the negative A sine T and dividing it by A. And then we're taking the A cosine T and dividing that by A. And you get negative sine T cosine T. Bless you.
Thank you.
Let's put it here this way. All right. So, this is a situation where you can kind of just consider, bless you, you can consider it in a slightly different way and come up with the same exact answer. So, the unit tangent vector for a circle of radius A. So let's think of it this way. How about we change the wording up a little bit? How about instead of the unit tangent vector for a circle, how about we say the tangent vector for a unit circle? All right, nobody's impressed by that. Okay, so
Cool, but it's like,
the unit circle has a vector valued function r of t is equal to cosine t sine t. All right, if I wanted the tangent vector to that, all right, that would be the same as the derivative, which would be negative sine t cosine t.
that is so cool.
See, that's what I was looking for. All right. So the idea here is, I mean, the unit part of it is talking about breaking it down to its base components. So in a circle, you're talking about a radius of 1. All right. What is a circle with a radius 1? It's called the unit circle. What are the characteristics of a unit circle? Well, going around the unit circle, which you've done a few times already now, you've practiced, you've done the bonus, and you've done the quiz, the coordinates are what comma what? Generally speaking. Cosine comma sine. All right, so this is the vector that would represent each of those coordinates around. If you were drawing a vector to each one of those coordinates around the unit circle, it would be cosine comma sine, just using theta instead of t. All right, so what we're getting from this is the derivative, which would be the tangent vector, negative sine t cosine t. Right, but if I'm looking at it in this context, it makes perfect sense because the unit tangent vector would be looking at a circle, just a circle. They all have the same shape and characteristics, assuming the center is the same. The base component of any circle would be the circle with radius of 1, the unit circle. All right? And so it would make sense that their tangent vectors would be exactly the same thing. All right? So that's your actual connection between all that trig stuff with the unit circle and what we were doing just in recent classes. Right? So moving forward, you could expect more connections like that. So why do I harp on the unit circle? Because it's going to keep coming back over and over and over again. And then eventually we're going to be thinking of coordinates in 3-space in terms of unit circle values. All right? Instead of saying 1, 2, 3, we're going to say 30 degrees, 20 degrees, and then maybe a height. If we're talking about cylindrical coordinates, or maybe we'll just do full angles all the way around. Right, so that would be spherical coordinates. Right, so the unit circle is never going away, and in fact, it's gonna take a shot of HGH. It's gonna get jacked up pretty good. Right, so we're looking at some good stuff related to the unit circle. Right, so well, actually, I guess it wouldn't be HGH. It'd be something else.
So funny.
Another dad joke, I guess. So anyway, you probably are wondering how this would relate to parabolas. And so that's reasonable in some capacity because at least you have the benefit of taking a look at it graphically. On the calculator it can handle 2-dimensional stuff. And this would just be a matter of putting your calculator in parametric mode and putting the first component in for the x and the second component in for y, and just putting reasonable t-mins and t-maxes in and see what it gives you. But it kind of saved you the need for doing that because it's a parabola. All right, so it's stated in the problem. Now the unit tangent vector is a vector that is tangent to the curve. Right, so we should be able to get a pretty good sense of the visual aspects of this without having to create a graph, because what a parabola looks like and a tangent vector shouldn't be too hard to conceptualize either. All right, but anyway, first thing we do is we figure out what r prime of t is. All right, so all we're doing is taking the derivative of each component. In this case, not too bad. We're looking at 2t as our first component and a 1 as our second component. Then we need the magnitude of r prime of t, our derivative vector, which is the sum of the squares of the two components rooted. So 4t squared plus 1. All right. Now t of t the tangent vector in terms of t, unit tangent vector, would be the ratio of our derivative vector to the magnitude of the derivative vector. So we're looking at 2t over the square root of 4t squared plus 1, comma, 1 over the square root of 4t squared plus 1. All right. And so in this case, that's all we're really looking for. Depending on the value of t, we can make a determination not only of a particular coordinate on the parabola, but also what the unit tangent vector would look like. All right. So it's giving us a sense of the direction of the slope, which is not an unreasonable thing to expect, because when you're talking calculus, you're not only just talking about location, but you're talking about a rate of change. All right. And so the vector that would represent the rate of change would be this vector. All right. Now, if you wanted to, you could do some substitution and figure out what your parabola equation would be in rectangular coordinates, just to get a sense of what it would look like, and then pop in a particular value for t to get a location, and then to verify this. But it's really a little bit beyond what the question's asking us to do. So at this point, it's just find the unit tangent vector. All right. So that's kind of a little bit of a warm-up. I know there were some starred problems prior to this, but this is the one that kind of sets us up for tonight's lesson, which deals with curvature. Opportunity to explore that. And so the next class, we'll get into the idea of curvature. And you could see that in a lot of cases, I mean, look at the formula. T prime of t, the derivative of the unit tangent vector. S of t, derivative of arc length, right? So having a good understanding of those concepts is going to go a long way to understanding the concept of curvature. So you have a week off. Not saying that you need to spend the entire week studying this, because I wouldn't, but you might want to dedicate a little bit of time. But before you even think about doing that, get that tech assignment in. All right, it needs to happen.
Midnight, right?
Midnight.
Yeah.
All right. If you find by the withdrawal deadline that your grade isn't what it's supposed to be or what you thought it would be, it's probably because you haven't been doing the tech assignments. All right, so get on that if you haven't done so already.
Or you've got like a 0 on the final.
All right, it's directly related to the concept of a unit tangent vector. All right. I don't think I ever explicitly stated this, but generally, when I type a derivation in the notes, it's not something I would ever ask you to do on a test. All right. Full disclosure, I type it because I can never remember it myself. And so if I can't remember it, I'm not going to ask you to do it. Right? It's the ones that we actually work through together on our own. Those are the ones that are fair game to be on an assessment. Right? Not that you are overly concerned about that right now, but just so I make sure I address it. Process for finding the curvature of a function. It's kind of weird, because you're thinking curvature is the idea that something has a curve to it. So wouldn't it be curvy or not curvy? Or like one or the other? Like if it has a curve in it, wouldn't that just exemplify the idea of curvature? And if it's a line, for example, it has no curvature. Yeah, but there's more to it than that, because you could find, for example, the moment in a graph where it has the most curvature. Like, for example, just off the top of my head, like a log function. It has a steep increase early on, and then it bends so that it eventually levels off as you approach infinity for x, if you're dealing with xy coordinates. There is some moment in time or some particular x value where it transitions from being really steep to being really shallow. That would be logically, seemingly anyway, the moment in which it has the most curve to it. So the curvature would be at its maximum. Right? So that's one aspect of this that could come into play. Right? But really, it's just we're looking for the bendiness of a particular function, and it will depend on where you are in the graph of the equation. So this particular formula helps us figure that out, and we have the general idea, which is the magnitude of the dt ds. All right, so that's the derivative of the unit tangent vector with respect to the arc length. All right, so that's talking about the ratio of the rate of change. Well, that is the rate of change. The ratio of the instantaneous change in unit tangent vector to the arc length. So the movement along the curve, the ratio of the unit tangent vector to every incremental movement along that curve. All right, so that gives us a sense of how bendy it is. This is some letter kappa, although I couldn't find any way to type the letter the way it's supposed to be, so I just used a funky looking K. I tend to draw it like this. Three parabolas, kinda. One sideways and two half parabolas. In the end, really, does it matter? Probably not. Just make a funky looking K, and you've created a kappa, in my opinion. All right. So, but I think this looks kind of cool. So I always encourage people to draw their Ks like this, and then just draw all your Ks like this forever. Not just the Ks related to this topic, but the Ks for the rest of your lives. It's a gorgeous looking K, and I fully support that K. All right, so that's what I would go with. That is the value that represents curvature. All right, so that's what we're looking for. Now, the derivation is played out exhaustively here, but basically we get to a shortcut formula, which is where we're going to live, because S of t is easy enough to work with if you're given S of t, but coming up with it involves integration and it's kind of a pain. But if we know through the fundamental theorem that we can use the magnitude of r prime of t as an approximator, well, actually an equivalent value of s prime of t, then a direct substitution can be made. So essentially what I'm getting at is the idea that all we need to do is find the unit tangent vector, take its derivative, find its magnitude, then take the magnitude of the derivative vector and divide the two, and we'll have some measure of kappa, right, which is the measure of curvature, right? So I say all you have to do. Well, I can list like 4 steps and make it sound like it's easy, but as you know, you have to carry out those 4 steps. So you will have to take the derivative of your unit tangent vector and then find the magnitude, which is as easy or as difficult as the values that make up your unit tangent vector. Right? If it's strictly numerical, it's not going to be that difficult. If it's completely in terms of function notation, aka in general terms, then it could be problematic. I'll show you real quick. Well, you know what the issue is that I had it set up for a split screen, and what it was doing was recording only the notes and not the split screen where I had a calculator on my iPad. So I'm trying something else. Anyway, so enter 2, because this is calculator speak for 2, because why wouldn't it be, right? So we have our first component as just a clean 2. Then we do the same thing. So second enter, no need to reinvent the wheel. Second enter brings up the previous calculation. You could also hit the up arrow and hit enter. This one should just be a 1, so let's just make that a 1. It still really just wants to look at my face for some reason. Memory overload. And there we go, we get a 0. Math option 8.
No, when you hit enter to go back in and edit the.
You hit the up arrow,
Yeah.
and then hit enter. Up arrow until you got it. Okay.
Thanks.
No problem. Now I have the issue of having nerve damage in my arms. Well, spine, really. All right, so 2, 0. All right, so No, you are capable of finding derivatives. It's not like I'm saying you can't do it. It's very doable. Quotient rule. You move this around a little bit and make it some chain rule, right? But like I can do this a lot quicker using this technique. So why wouldn't I utilize my resources, right? So it's not like you're avoiding demonstrating the knowledge of calculus. You had to do it in Calc 1. You've already been assessed on it. You don't need to do it anymore, right? Or at least that's my opinion. Right? So t prime of 0, that's good. Got that. I need r prime of 0 as a magnitude. So let me set that up over here, and let me bring it in a little bit. That way you just crank it out. I mean, there's no point in showing any work. Just plug in a 0 for t, it's going to become a 1. All right? It's a magnitude, so it's an absolute quantity. So you get a 1 there. All right? So what we're looking for, again, just going back to the rule, is t prime of t. If I needed it in general terms, we would have to do all this stuff. If it's not at t equals 0, you would have to find the derivative, and you would have to divide it by, square it, add it together, and then divide. But here, that's not the case. All right. So what I need in order to find my kappa is the magnitude of t prime of 0 over the magnitude of r prime of 0. All right. So I need the magnitude of t prime of 0. Well, that's just 2, right? So you don't need a formula for that. And then divided by the magnitude of r prime of 0, that gives us a result of 2. All right. I tend to think of curvature, kappa specifically, as kind of along the lines of standard deviation in statistics. 0, if I just talk about standard deviation for a second, 0 means that the data are not spread, right? It means that they're all exactly the same, right? So there's no deviation whatsoever. Everything else indicates some level of spread, right? The larger the number, the more spread out they are, right? That's the same idea here. The larger the number, the more curvy it is. So it's a question of, okay, well, how curvy is curvy enough? Well, it all depends. In most cases, we're looking for it as a comparative measure, right? So I would be looking for you to determine which one has more curvature, this parabola or maybe a sine function or maybe a circle. I mean, I think you probably figure that the circle would be more curvy because by definition, that's what you think about when you think of a curve. But everything is relative. Right? So as long as you have that in mind, 0 is absolutely no curve whatsoever, so that would be the case of a line. Everything else is going to have some curviness to it. It's just how does the curvature compare from one function to another? That's really all we're after, Christian.
I thought for this step you would have to square it, add it, and square root it. Why did we do that?
Well, we kind of did, but because it's on an axis, it's just the absolute distance. That's really all a magnitude is. If you square them, add them, and then square root it, you're going to get back to a 2 anyway. Right? So if you're on an axis, generally all it is whatever the linear distance is. So let's say I'm on a three-dimensional plane, and I'm looking at a coordinate 0, 0, 9. I can add them all, square them, add them all up, and then take the root, but it's just going to bring me back to a 9. It's just a distance from the origin.
How would the general form look like for the curvature in terms of, like, in this problem?
In a word, disgusting. Yeah. So you'd have to take the derivative of each part of these, square that result,
Yeah.
add them together, then take the square root, and then divide by this number.
Wow. Okay.
It's algebra intensive. Very doable, but a lot of algebra involved.
And would you ask that, like, during the test? Like,
No, it would take up like half the test. Yeah, that's how lengthy it can be. Like you'd get bogged down in just the algebra to try to do something like that it wouldn't even be worth it. You're demonstrating just as much knowledge with a question like this as you are doing it in general terms, that I don't feel the need to ask you to do it that way. All right, so, that being said, here are some cases where there's some general terms, but there's a reason why these are structured the way they are. Find the curvature of a circle of radius A in R2. All right, so two-dimensional situation here. What I'm looking at, if I'm dealing with a circle, is something in the form of A cosine theta, comma A sine theta. All right, coefficients should be the same, all right, because they represent distance. All right, so following the process, and the reason why I can ask these questions rather than like in the last case is because these are very, very clean. All right, if I find r prime of t, I'm looking at, so just a derivative, we're looking at negative a sine theta, a cosine theta. The magnitude would be the sum of the squared values. So a squared sine squared plus a squared cosine squared, drop the negative. We have a GCF of a squared that can be rooted out of the whole thing, giving you an a times the square root of sine squared a plus cosine squared a. Oh, I forgot my theta. And sine squared plus cosine squared is equal to 1. So a times 1 is a. All right, so if I'm looking for the unit tangent vector, I'm looking at t of t is going to be equal to negative sine theta, comma, cosine theta. All right, because all you're doing is taking your r prime of t and dividing it by its magnitude. All right, so that's nice. Really, when you think about it, I mean, the unit circle is defined as cosine, comma, sine. Okay? So with a coefficient of 1. So that's why it's unit. It's a unit circle. It's of a single unit. Radius is equal to 1. Right? So it makes sense that this would be the derivative of whatever the original function would be with a radius equal to 1. Right? So that's the definition of a unit. So now we have to go through the more interesting part of it, which is to find the derivative. So t prime of t. All right, in general terms, but still not bad because we're working with basic trig function sines and cosines. So the derivative of negative sine is negative cosine. Derivative of cosine is negative sine. I need the magnitude of that. Drop the negatives when you square them, obviously. But cosine squared plus sine squared is the same as sine squared plus cosine squared, so it's going to be 1. Square root of 1 is equal to 1. All right, so the magnitude of the unit tangent vector is going to be equal to 1. Now, when I want my kappa, I'm going to take that 1 and put it over the magnitude of my derivative function, which we determined was a. All right, so kappa is going to be equal to 1 over a. All right. Now I'm just going to make a little note here where A, you don't have to write this, I'm just doing this just to kind of bring it all together, where A represents the radius of the circle. And so what we get from this is the idea that the curvature of any circle is always going to be 1 over its radius. Okay?
Why aren't all circles equally as curvy?
So little circle, if you're traveling around just tracing it with a ruler, for example, really got to kind of like bend that ruler as you go. But if you have a ginormous circle, you can leisurely move that ruler as you go around. So a large circle, a very, very large circle, like some segments of that could almost appear linear, right? And so what this gets at is the idea that if you have a circle with infinite radius, right? So just imagine that, like a circle that's increasing in size, becoming so substantial that, you know, like you're standing on, you know, a circle right now. You know, we create things that look linear all the time, but they are on the surface that has a curve to it. But the circle, or, you know, the path along the sphere is so large that everything appears linear. What you're ending up with is something that definitely is less curvy than something that would be much, much smaller, right? So that's the idea that, you know, like if you were to limit this, for example, and say the radius is approaching infinity, what would my kappa be approaching? 0, right? So if you could ever apply infinite radius, what you're creating is something that would become linear, right? If you could actually get to infinite radius, right? So you want to be thinking like small circle versus a galaxy, you know, like the circular boundaries of a galaxy. If you're looking at any sector of that, actually that would be a segment, but if you're looking at any portion of the circumference on the boundary of a galaxy, it would appear linear, right, just based on the size of it. All right. So the next one, you know, same general idea, except you're dealing with something in 3 space. And it's got a little bit more, or a little bit of a different sort of feel to it. But then the curvature for any straight line in R3. So I'm going to put a star on number 11. Number 12 I'm actually going to get you set up on, because step 1 on this is probably the hardest thing. And then after that, I think it'll all kind of make sense from there. So we want any straight line in R3. So I need 3 components. Any of which could be a linear function. All right, so when we're dealing with a vector value function that is a line, any or all parts, any or all components of that vector value function could follow the model y equals mx plus b. All right, but we could have 3 distinct m's and 3 distinct b's. So we need to distinguish them from one another. All right, and also we're working in terms of t here, so we might say something like m sub 1 t plus b sub 1, m sub 2 t plus b sub 2, m sub 3 t plus b sub 3. The good news is, well, derivative is going to be pretty easy, because we know the derivative of a linear function is just its slope. So that gets you to m sub 1, m sub 2, m sub 3. And the magnitude, also pretty easy. I mean, to carry out the process, you're not going to be able to figure out anything numerically from this, but you can make the determination that the magnitude would have to be m sub 1 squared plus m sub 2 squared plus m sub 3 squared. the unit tangent vector, wow, that's not going to be pretty. But what results from it will be, actually let me go a little higher here. And I know I said I'd get you started on it, but I'm actually just doing the whole thing right now. In case anyone's wondering. So each component of R prime is going to be put over your magnitude.
Would it be wrong if you put the magnitude once and then the 3 ends with commas? So everything, yeah.
No, it wouldn't be wrong. That's fine. The next step is finding the derivative. So it depends. In this case, it's not going to matter one way or the other. But depending on the nature of this vector value function, you may need to end up in this format one way or the other. But in this case, it doesn't matter at all because t prime of t is equal to what? Nice round number. What do we say? Do you see any t's in there? So what is the derivative? 0. Nope, I put one too many. Exactamundo. All right, and so then what would be the magnitude? Magnitude would be equal to 0. And so therefore, what would kappa be equal to? 0. 0 because it had to be, because it's a straight line, but also because the kappa formula has t, the magnitude of t prime of t, as its numerator. So unless the r prime of t magnitude is also 0, which it's not, right? Unless you were dealing with something, some linear functions, a set of linear equations in which all 3 slopes were equal to 0, in which case it would not be a straight line. It would be the 0 vector. Well, actually, it wouldn't necessarily be a 0 vector, but it would just be a numerical vector. It wouldn't be a vector value function. It wouldn't be a line. That's one thing I can say. You're looking at something that's going to be 0 over some real number, in which case result is equal to 0. All right. So number 13 we skip. I always have that one in there because if I run into a class that I really dislike, then it becomes required knowledge, but that is not the case here. And so we don't do